Welcome back. In this video lecture, we're going to cover section 2.2 of the textbook, One Quantitative Variable, Shape and Center. I've divided this section into 5 subsections. We're going to look at quantity, shape, mean, median, and resistance. Mean and median are two what are called measures of centers. They're ways of taking an entire data set and summarizing it in a single number, which is in some sense supposed to capture the essence of the data set. So we'll look at those two measures of center, and then we'll compare them through this topic of resistance. All right, that'll be the last thing we'll look at in section 2.2. So let's go on and study quantity. At this point in the course, when we think about a quantity or a quantitative variable, I want us to concentrate on 3 important questions. And these revolve around the concepts of shape, center, and variation. Now, 2 of these, shape and center, we'll talk about extensively in this section, and we'll save the concept of variation for the next section. But it doesn't hurt to think about it a little bit already in this section. So the first question, what is the general shape of the data? And this question is going to be answered through either a dot plot or a histogram. And we're really getting at the kinds of questions like this. Is there a central axis on which I could fold the dot plot or the histogram and it would fold on top of itself? So that's the question of symmetry. Is the dot plot or the histogram symmetric? Is the data symmetric? Does it have one mode or does it have several modes? Does the data push off to the right or does it push off to the left? That's the question of whether it's skewed to the right or skewed to the left. We're going to want to be able to look at a histogram or a dot plot and very quickly kind of categorize it in this way, right? We want to be able to assess the shape. Why? Because according to how the data is shaped, that's going to, no pun intended, shape the kind of analysis that we can do on the data. Okay, so we want to have pay some attention to the shape of the data and be able to classify it. All right, where are the values of the data set centered? There's 2 primary ways of talking about the center of the data set. One is the median and one is the mean. These are really getting at the question, could I, if I had to summarize the entire data set in one single number, what would be a fitting number to attach to that data set? And again, historically, this has been done through the mean and through the median. Okay, final question. How do the data vary? This is a topic for the next section, but let's think about the question now. Once you've established the center of the data, we can now talk about how far each individual data point is removed from that center. Some of the data points might be very close to the center, and some of them may be very far removed from the center. And so the question is, what is the measure of that average distance of the data points to that center that we've established? And that's captured by this notion of standard deviation. So it's a single number that kind of expresses how tightly packed or how widely dispersed all the data points are from the center that we've established. Okay, so we'll look in more detail at shape and center in this section, and we'll take up variation, standard deviation, in the next section. Now, before we get too far afield, I want us to open up StatKey, load a file into StatKey, a quantitative variable. In this case, we're going to look at mammal longevity. And I want us to look at a series of questions associated with that file. I want us to think of this as a kind of a treasure hunt. It's a way of kind of getting started thinking about how StatKey is going to represent the data set to us and having some confidence that we can pull information out of the graphical plots and the summary statistics that it gives to us. All right, so let's look at the kind of questions we're going to want to answer. All right, what is the size of the sample? What is the range of the data? So what is the difference between the maximum value and the minimum value in the data set? What is the most common lifespan of the animals? Approximately where is the center of the data? Which data points seem removed from the rest? That's the question of outlying values. We want to look at the corresponding histogram, and we want to answer the question, what is the difference between a dot plot and a histogram? By default, StatKey always gives you the dot plot, but there's a little tab that we can click on to present us with the histogram instead. And we're going to want to see how those two are related to each other. Okay? When we look at a histogram, it is going to resemble a bar chart. A bar chart is the appropriate graphical representation for a categorical variable, and a histogram is doing some of the same kinds of thing, but it is what's appropriate for a quantitative variable. All right, and so we'll want to know, how is a histogram different from a bar chart? All right. Question 8, final question, is what is the effect of changing the number of buckets in the histogram plot? All right, so what is the number of buckets doing in a histogram plot? All right, now what I want to do next is go to StatKey, load that file, and just run through these questions and see if we can pull them out. So when we go to StatKey, we're now going to be working with a quantitative variable, and we're going to be looking at descriptive statistics associated with that. So we're going to go into this column of descriptive statistics and graphs, one quantitative variable. And the file we're interested in is mammal longevity. That is the default file when you start with descriptive statistics for one quantitative variable. If we were interested in a different file, of course, we could click on this list and find other files that we could load in its place. But we're interested in mammal longevity. Now let's just take a quick look at the data table just so we can get familiar with what's going on here. There are a number of different animals, and for each animal, the baboon in particular here, we're going to see that it's got an average lifespan of 20 years. By comparison, the black bear has an average lifespan of 18 years. So we've got all of these different quantitative values associated with these various cases, these various animals. And one of the things that StatKey is going to do is it's going to present us with a graphical display of that data, and it always defaults to the dot plot. And what is a dot plot doing? Well, if I mouse over one of these values, you can see that since the tiger has an average lifespan of 16 years, it's going to plot a dot at 16. Now, there's a variety of animals that share this 15-year average lifespan, so StatKey simply stacks them on top of each other. Okay, so there's a graphical display of the data set called a dot plot. Now, what is the size of the sample? We could get at that by 3 different ways. We could look at the data table and count the number of rows. Not particularly pleasant thought. We could count the number of dots in the dot plot, since each case is appearing as a dot in the dot plot. Again, that doesn't sound like a whole lot of fun. Or we can simply realize that StatKey already pulls that number out and summarizes it here for us. So the sample size is 40. There are 40 animals in this data set. All right. What is the range of the data? What is the maximum minus the minimum? Again, we could get that from the data table by examining the columns. We could pull that out of the dot plot by looking at the maximum and minimum. So the elephant and the opossum gives us a span of 39 years. Or we could just simply look at the summary statistics and see that the minimum and the maximum are sitting there waiting for us to use them. Okay? All right. The following question is not typical for a quantitative variable because they don't necessarily have to line up on integer values, but since these are all integer values, we can ask this question: what is the most common lifespan? Okay. Since all of the answers are being reported in integers, we can look to see that the most common lifespan is this 12-year lifespan, and that's shared by a number of different animals. Coming in as a close second is the 15-year lifespan, again shared by a number of animals. Okay, and that's called the mode. Approximately where is the center of the data? There's 2 different measures of center that we're typically going to be interested in. One is the median, which puts the center at 12. So right here, where I've put the mouse, it's saying that's one measure of center. And the other one is the mean, which again is in the list of summary statistics, and it's putting the center at 13.15. So by one measure, the center is about 13.15. By another measure, the center is at 12. But in both cases, we see that those are roughly, they're very close to each other, and they're both ways of summarizing the entire data set down into a single number. Okay. Which data points seem removed from the rest? Well, this is, again, somewhat subjective at this point. We'll have a technical way of addressing this in the near future, but when I'm looking at this, I really see that this clump seems to hang together fairly nicely. There's a bit of a gap here between the hippopotamus and grizzly bear at 25 years and these animals at 20 years. There's a 5-year gap, but there's a tremendous gap here between the grizzly bear and the hippopotamus and the elephant, right? That's a very large gap. And so this elephant at 40 years seems very unlike all of the other mammals. And so I would be very suspicious that that elephant is an outlying value, right? Something that's different from the rest of the data set or unusual in the data set, okay? Look at the corresponding histogram. What is the difference between a dot plot and a histogram? So remember, in a dot plot, every single case is there. We're seeing 40 dots because there are 40 cases. Now, when I go to the histogram, we see that some information is being compressed, okay? What is a histogram doing? It's basically taking the x-axis, it's chopping it up into a number of bins of equal width, okay? And they are lying one next to the other. So these bins are butted up against each other. And it's basically saying, if your average lifespan fits inside this first range, in that first interval, then I'm going to throw you into this bin and count you. And so we can see that there are 3 animals that fit inside this, or whose lifespans fit inside this first interval. Okay. Now, if you want to know what that interval is, I'm going to have to ask you, I'll take the mouse over here. Pay attention to the values that populate this array here when I put the mouse over the bucket or over the bin. All right. So when I hit that bar, you can see over there that the lower bound is 1, the upper bound is 4.9, and there are 3 that fit inside that range from 1 to 4.9. So 3 of the animals fit between the range of 1 and 4.9, and therefore the count for that first bin is 3. If I mouse over to this next one, we see that that bin covers a range from 4.9 to 8.8, and there are 8 animals that fit into that range. And you can kind of work your way across the histogram bar by bar. So what is a histogram doing? It's making counts. It's counting the number of data points that land between a left endpoint and a corresponding right endpoint. Okay? Now, strictly speaking, we've lost some information, right? We know that there are 12 animals that sit inside this bin between 8.8 and 12.7. But we can't recreate from that number 8 exactly where those data points are. So technically speaking, in moving from the dot plot to the histogram, you are suffering a loss of information. Now, one thing you need to understand, though, is that once a data set gets very, very large, the dot plot becomes somewhat meaningless. It's hard to digest all of the information that's carried in a dot plot, and it's actually more helpful for our brains to access that information in a somewhat compressed way. So there's some usefulness in taking some of the data and collapsing it in this way and presenting it to us in a kind of a compressed format. You just have to understand that you can't recover the original data set from the histogram. We've, strictly speaking, lost some information. Okay. Let's look at this question. How is a histogram like a bar chart, and how is a histogram different from a bar chart? Well, it's like a bar chart in the sense that it's making counts and it's presenting the counts to us in a bar. It's different from a bar chart in that a bar chart is corresponding to a categorical variable, and when I'm looking at a bar chart, I am free to imagine permuting the bars, changing the order in which the bars are presented to us from left to right, and I don't feel like I've lost any meaning, right? Because it's just those are pure categories. On the other hand, when I'm looking at a histogram, I have to understand that these bins that are being represented by these bars are on an ordered number line, and therefore I am not free to take, for instance, this bar and exchange it with that bar. I cannot permute their ordering within this diagram without completely destroying the information that's being conveyed, right? So the ordering of these bars and the fact that these bars are sitting right up next to each other is reflecting the fact that we are partitioning this interval into a series of equal length bins that are buttered right up next to each other. Okay, so it does look like a bar chart, but it is really conveying some different information. Okay, so what is the effect of changing the number of buckets in the histogram plot? Okay, so when I go over here and change the number of buckets from, let's say, 10 to 5, you can see the effect, right? I'm basically making these bins wider, and in some sense, in a very strict sense, I've lost some information. So when I mouse over this first bin, I can see, again, by looking over to the left into that lower left array, I can see that that lower boundary is now extending from 1 to an upper boundary of 8.8. So any animal that has a lifespan between 1 and 8.8 is now being thrown into this bucket. And I can see now that there's 11 animals that fit into that bin from 1 to 8.8. As I mouse over to the next one, it's going from 8.8 to 16.6, and there are 20 animals in this. So again, it's doing the same work it's doing the work that a histogram does, but in some sense, because I've reduced the number of buckets, I've lost more information. Okay, if I increase the number of buckets from, let's say, 10 to 20, the obvious thing has happened, right? This first bin now goes from 1 to 3, and there's only one animal in there. All right, so this is actually retaining much more of the original information that was in the dot plot. Now, what's the right number? Well, there's no answer to that question. There's no answer to what is the right number of buckets. The real question is, well, the thing to understand are the extremes. If I have too few buckets, if I just have one bucket, then there's no point, right? All I know is that there are 40 animals in my data set, and I knew that already. If I use too many buckets, right, if I go all the way to 40, I have just recreated the dot plot, right? I've got all the information that was already in the dot plot. And I've lost some of the beauty of the histogram, which is to compress some of the information and present it to me in a way that allows me to kind of see through the data, all right? So I do want a little bit of compression. I just don't want too little and too much. So with every quantitative variable, you'll just have to keep adjusting the number of buckets until you feel like the right level of compression has been achieved, right? So we want to be able to assess the shape of the data. We don't want too few buckets, and we certainly don't want too many buckets. So what the right number is essentially an unanswerable question, but I do feel like some values, some number of buckets are better than others, and I think 10 is a fairly nice number for this data set. Okay, that kind of brings a conclusion to our little foray here into StatKey and our work with this one categorical variable. We finished this kind of initial subsection on quantity, so what I want to do now is take us into the next section on shape. So when we talk about the shape of a distribution, what we're really doing is we're talking about the shape of, let's say, the dot plot or the shape of the histogram. And what we're going to do is learn 4 different ways of talking about the shape of a distribution. We'll have 4 different categories in which the shape of a distribution can be placed. What I want you to bear in mind, though, is that when you look at some actual data, when you look at some data from the real world, it is going to be very hard to classify perfectly. So you have to allow yourself some wiggle room here when you work with these categories. All right, so what are the categories? We really have 4 different ways to describe a distribution, right? We can say it's symmetric if the 2 sides of the distribution approximately match when folded on a vertical center line. So we can imagine imposing a vertical line through our dot plot or through our histogram, folding along that vertical line, and we can imagine the data folding on top of each other. All right? We're going to say that the data is skewed to the right if the data are piled up on the left and the tail extends relatively far out to the right. Likewise, the data is skewed to the left if the data are piled up on the right and the tail extends relatively far out to the left. And finally, we're going to say the data are bell-shaped if the data are symmetric and, in addition, have the shape of a bell. Now, the best way to get into this is just to look at some shapes here and see if we can practice classifying them. All right, so if we look at this first situation, what we're noticing is that the bulk of the data, right, if this were the dot plot or the histogram, the bulk of the data is sitting here on the left side. But we do have some data spilling out to the right, so we would definitely want to classify this as skewed to the right. So remember, when we talk about the direction of skewing, it's the direction of that tail. Here we have the opposite situation. We have the bulk of the data sitting on the right, and we have a tail extending out to the left, so we would call that skewed left. In this situation, we have a symmetric distribution. We can imagine a central vertical axis here. We can imagine folding this shape on that axis, and it would fold on top of itself. But in addition, it also has the shape of a bell, so we would categorize this one as bell-shaped. Finally, this one also has a symmetry, right? There's a vertical axis along which we could fold this distribution. We could imagine it folding on top of itself. But the difference between these two is that this does not have the shape of a bell, so it is symmetric but not bell-shaped. In fact, we might call this, if we wanted to, we would call it M-shaped. But it definitely has these two pronounced modes and is not going to be a bell-shaped distribution. All right, so let's just review before we leave. We've got skewed to the right, skewed to the left, symmetric and bell-shaped, merely symmetric. Okay? Now, what I want us to do is to go in to StatKey and look at some real-world data. The first data set we're going to look at is called Student Survey TV Hours. And basically what that is some college students were asked to respond to the question, how many hours of TV do you watch each week? So we'll take a look at that data set and try to classify it. The next thing we're going to want to do is upload a file. This one's not built into StatKey, so we'll see how to upload that file. We'll bring it into StatKey. That file contains lots of data, some of it categorical, some of it quantitative. We're going to want to select the variable called pace, and what that's going to do is give us the per mile pace that each of the runners had either in their half marathon or their marathon. And we're going to want to take a look at the shape of that histogram and try to describe it as best we can. All right, so let's go ahead and head over to StatKey and let's load the file, Student Survey TV Hours. Okay, there's the dot plot, and here's the corresponding histogram. And if we were going to try to describe this shape, we would notice that the bulk of the data is over here on the left. And there is some of the data pushing off relatively far out to the right. So we would classify this as skewed to the right. Now, what does this mean in the context of this data set? That what this means is that probably, most of the students, right, we could get an exact count here, but most of these students are watching relatively little TV per week, but there are a few people who are watching a lot of TV each week, and so those people are pushing this data set out to the right. It is skewed to the right. Okay, now for our Spinks RunFest data, we're going to have to upload a file. So we're going to have to go to the upload a file, and I've got the 2019 Spinks RunFest data sitting here, and I can select pace as my variable of interest. Okay, now we're looking at this distribution, and we're trying to see how we could classify it. And if we had to put it into one of the categories, I would call it bell-shaped. But you can see the problem here. It's not perfectly bell-shaped. It is skewed a little bit to the right, so it does not conform perfectly to a bell-shaped distribution. But if I had to put it into one of the four categories, that's how I would classify it, as bell-shaped. Now, one of the things that I'd be interested in we can do this later in the course when we look at interactions, I might be interested in seeing what the shape of the distribution would look like if I just looked at the half marathon people, Or what would the shape of this distribution be if I just looked at the marathon people? It could be that this little extra mode that we're seeing here is the effect of mixing in some marathon runners who are moving at a slightly slower per mile pace. So that would be something to explore in the future. But for now, if we're just trying to put this into a broad category, I would call this roughly bell-shaped. Okay? Now, that covers the idea of shape. We've got our categories for describing shape. We've practiced looking at some real-world data and describing the shapes of that data. So our next topic is to discuss our first measure of center, and that's called the mean. So let's take that up now. The mean of the data values for a single quantitative variable is the numerical average of the data. That is, you simply go through the data one piece at a time and you add them all up. You get the total sum of the data values, and then you divide by the total number of data points. We'll use this shorthand notation for this action. So sigma just means sum. Sum all of the data and divide by the total number of data points. So this is literally the numerical average of the data. Now, as far as notation goes, there'll be two ways to notate this depending upon the context. So the mean of a population is denoted by mu, whereas the mean of a sample is denoted by, let's say, x bar if the variable is called x, or y bar if the variable is called y. So we'll have to know if we're referring to a population or a sample to know how to properly notate the mean. But the action of calculating a mean in either case is simply to calculate the numerical average. Now, let's take a look at how we can think about this mean geometrically. So we should be able to look at a histogram, or we should be able to look at a dot plot and have some sense of how we can picture the mean fitting into that dot plot or its histogram. And so here's one way to think about it. We can think of the mean as the center of mass of the data. Let me give you a visual aid here, right? Imagine I've got 6 children on a teeter-totter or a seesaw. Let's imagine that the seesaw actually has a ruler imposed on it, so marking, some way of marking where the children are. So what I've got here are these 6 children at positions 2, 3, 4, 5, 10, and 12. And the question is, where would the balance point for this seesaw be? Where would I put the fulcrum in order to keep these children balanced? It turns out that if you simply compute the mean of their positions, so simply compute 2 plus 3 plus 4 plus 5 plus 10 plus 12, and divide it by 6, I get 6. And if I place the fulcrum at 6, the system will be perfectly balanced. These children will be balanced on the seesaw. So one way to think about the mean is to think about it as the center of mass for the system of masses given by the data. All right, so you should be able to look at the histogram or look at the dot plot and imagine that those are children on a seesaw, and you're asking for the balance point or the center of mass of that system. Okay? Now, how would I actually compute it? Well, let's imagine the following situation. So a professor gave an exam to his Math 450 class, and here are their scores. And you can see that there's a range of scores here. I think there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in total. All right, if I wanted to compute the mean of this data set, there are several things that I could do. I could just use good old-fashioned paper and pencil and try to work it out that way. I could use a handheld calculator. I can use an online calculator, or I can bring the data into StatKey and have it compute the answer for me. So let's take a look at using a calculator to do this. And there's a nice online tool that we can use. And this is the Desmos Scientific Calculator. And I can simply, what I did here to do this calculation is I used some parentheses to encase the numerator. I typed in all of the data from that data set. You can see it's strung out here. I just simply added it all together. Then I divided by 12, and I got 78.83 for the mean of that data set. Okay, so that's one way to do it. You can use pencil and paper. You can use your handheld calculator, or you can bring the data into StatKey. Let me show you how to do that. Now, if we want to use StatKey to find the mean for this, There's a couple of different things that we could do. So one thing would be to just type this data directly into StatKey, or I'll show you the way. I'm just going to bring up a little text tool. I'll just type the data into that little tool, and then I'll copy it and paste it into StatKey. Or you could create an external file and load that external file, just like we did the Spinx RunFest data. Let's do this method here where I just get the data typed into a text editor, and then all I have to do is, and I want to make sure that it's in a single vertical column. I'm just going to take that vertical column, highlight it, and copy it. And then what I'll do is I'll open up StatKey, and I'll go to one quantitative variable. And here's the part of it that's a little non-intuitive. I want to go to Edit Data. I want to basically erase all of the data that's in an existing data set. And I want to replace it with the data that I've just clipped out of that text editor. All right. Now, I have to pay attention to a couple of things, right? The first column is identifier. That's a no. I don't have an identifier column. That would be like in the mammal longevity. That would be the name of the mammal that's corresponding to the longevity. I don't have that. And my data does not have a header row. I don't have a descriptor at the top of this column describing what that data is. So I'm going to say no. And then when I click OK, I'm going to get the dot plot from my data. But the most important thing is I just want to go over here and read off the mean at 78.833, which is exactly the same thing we got using the Desmos scientific calculator. So if my data set were quite large, this is exactly what I would do. All right, so we've got various ways to compute the mean, and they all kind of amount to the same thing. So just kind of choose your method accordingly. The one last thing we want to make sure we answer, though, for this problem is, should we use mu or should we use x bar to notate this mean? And here the question is, are we thinking of this Math 450 class as a population in its own right? If that's the case, then we should think of this as being notated by mu. All right. On the other hand, we could think of this as the current Math 450 class in the stream of an ongoing set of more Math 450 classes. And so we could think of this as a sample from a larger stream of Math 450 classes, in which case we would notate this by x bar. So it's really just the question of whether we're thinking of this as a sample or a population. Okay, now that's our first measure of center. That's the mean, and it's basically the numerical average, and we can think of it as a center of mass. The next topic that we want to take up is the topic of the median, which is a second way of measuring the center of the data set. So rather than give you a technical definition for the median, I think we can convey all you need to know by looking at a couple of simple examples. Now, what we're going to see in both cases is the median is a single number that has the action of splitting the data set in half. All right, it cuts the data set into a lower half and into an upper half. And the only thing we have to pay attention to when we're going to calculate a median is whether or not the data set contains an odd number of elements or an even number of elements. Let's look at the odd case first, because in some sense that's the easiest case. So the first thing I need to do when I have my data set, in this case this data set contains 9 elements, is I need to sort them from least to greatest. Okay, so I've done that already. Here my data set extends from 1 up through 12, and everything is sorted in between. Since there are 9 elements, there is an element that sits in the middle of this sorted list, and it's either 5 from the bottom or 5 from the top. Either way, the element 6 sits in the middle of this data set, and so we're going to announce that 6 is the median of this data set. Okay, it's the middle element of the data set. All right, when your data set has an even number of elements, here's an example of a set S2 that contains 8 elements. Again, once the data set is sorted, I'm looking for a number that splits the data set into a lower half and into an upper half. But since the data set has an even number of elements, in this case 8, there is no element that sits in the middle. So what we do instead is we say, well, since there are 8 elements, there's going to be a lower 4 and there's going to be an upper 4. And what I should do is find the largest element in the lower 4, the least element in the upper 4, and average them. And so I will announce the median of the set S2 is 7 plus 8 over 2, or 7.5. All right, so we're thinking of 7.5 as the number that splits the data set into a lower half and an upper half. Okay, so the couple of things to keep in mind when you're computing medians is you have to get the data set sorted, and then you have to figure out whether there's an odd number of elements and do the technique that's appropriate for the odd case, or an even number of elements and do the technique that's appropriate for the even case. Now, what I want to do before we go on and do some calculations is to compare the mean and the median by bringing back that graphic that I had earlier when discussing the mean. So if you remember, we had the 6 children balanced on the teeter-totter. The mean of 6 was acting as the fulcrum of that seesaw. And so that's our interpretation of the mean. Now, if I want to compute the median of the positions of these children, remember this data set contains 6 children, so there's going to be a lower 3 and there's going to be an upper 3. And since it's even, I'm going to take the 4, the top element in the lower 3, and the 5, the bottom element in the upper 3, and I'll find their average. So in this case, I see the median is 4.5. So hopefully by putting these two together in this one graphic display, we can see that the mean and the median are both measures of center for the data set, but they're doing very different things, right? One is acting as a center of mass, whereas the other is simply saying this number, 4.5, cuts the data set into a lower half and an upper half, okay? So remember that. Remember this picture when you're thinking about the difference between the median and the mean. Okay, now what I want to do is I want to go and do a couple of calculations, and I'll do these using the overhead camera, and I'll show you how to do these in real time. I think that'll be easier than trying to do it on the screen here. But what I want us to do is take a look at a set S and a set T and compute their medians. And one of the things that you'll notice about these sets is that they don't come to us ordered. So one of the techniques that I want to show you is a simple technique for getting the data into an ordered array, and then we'll find the medians accordingly. So let's go ahead to the overhead camera and take a look at how to do these two calculations. So our job is to find the median of this data set S given here, and as we can see, this set has 12 elements. Once I get this set ordered, it's going to be relatively easy to find the median of this data set. So what I'm going to show you is a technique called a stem and leaf plot. In fact, an ordered stem and leaf plot. It simultaneously orders the data set, but it also gives us a nice visualization of the data set at the same time, so it's kind of a bonus. So let me show you how to construct a stem and leaf plot. The first thing we need to do is to scan our data set and see the range of possible tens digits for our data. And as we look through this data set, we can see tens digits ranging from 6 through 9. So I'm going to write the numbers 6 through 9 in a vertical stack right here. And I'm going to put a vertical separator. Now, every element in the data set is going to be composed of a tens digits and a ones digit. I'm going to use the tens digits here to reference a row for the number, and I'll put its ones digit on the right-hand side here. This will be easier to see than it is to explain. So, for instance, if I want to represent this number 95, I'm going to use the 9 and then the 5 to represent the 95. If I want to represent the number 74, the 7 and a 4. The 98 will go in the 9's row as 9 and 8. The 70 will go here. The 70 will go here. And I'll continue to fill this out without comment. Just watch it, watch the array fill out. Okay, so I've got my stem and leaf plot filled out. Now, in the language of stem and leaf plots, These are called the stems, and the ones digits are called the leaves. And every element in the set S is now represented in this array. I'm going to show you the next step, which is now to order the array. Now, before I do that, let me just do a quick check. I want to make sure that I haven't lost anything along the way. I'm just going to do a quick count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I still have 12 elements. I feel pretty good that I haven't lost anything in the exchange. Now, what I'm going to do is redo this now, but now in the ordered fashion. So let me rewrite the same stems. Now all I have to do is order the numbers within the rows. So in this case, the 5 will come before the 9. And I've got both of those taken care of. The smallest numbers in this row are the 2 zeros, and then the 2, and then the 3, and then the 2 4s. I have nothing in the 8 row. Down here in the 9 row, I'll have a 3 and a 3, followed by a 5, followed by an 8. Okay? And so this gives me the ordered stem and leaf plot. Sometimes called the plot, sometimes called the diagram. I mentioned that this also gives you a visualization of the data set, because if you look at this sideways, it gives you an accurate picture of the data as a histogram, where the bins are of size 10, okay, or of width 10. So you get a beautiful visualization of the data set, and now you can see that we have a perfect ordering of the data set, ranging from the smallest number in our set is 65, and the largest number in our set is 98. Now, the rest of the game is pretty easy. Now that we've got our set ordered, we just have to cut the set into 2 equal pieces of size 6. It's an even ordered data set, so I just have to count 1, 2, 3, 4, 5, 6. There's my lower 6. 1, 2, 3, 4, 5, 6. There's my upper 6. My median is this number that cuts the set into those 2 equal pieces, and we know in this situation we're going to take the average of 73 and 74. So we're going to announce that our median is 73.5. And that's it. We'll move on to the set T now and see how it can be handled using exactly the same technique. And now we want to find the median of the data set T. Now, I've done some of the work ahead of time just to spare you some of the gory details. I took the data set T, noticed that it has 11 elements, an odd number of elements. I did the stem and leaf plot, just taking the data as it came to me, and then I formed the ordered version of that stem and leaf plot. So now I have the data arranged from the smallest number of 43 to the largest number being 56. And now my goal is to just identify the median of this data set. This is the particularly simple case where the length of the data set, or the size of the data set, is odd, in this case of size 11. To find the middle of that data set, I simply add 1 and divide by 2. So 11 plus 1 is 12, divided by 2 is 6. I just have to find the element that's either 6 from the top or 6 from the bottom. Either way, it gets me to the same point. So let's count. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. It doesn't matter how you do it. You're going to get to the same place. So we can simply identify the median of the set T as the number 52. So what these last 2 examples will show you is that if you have to compute a median quickly by hand, and if the set is not too big, but it doesn't come to you ordered, you can order it using a stem and leaf plot. And that's a very simple way of kind of getting the data ordered up so that you can very quickly find the median in either the even or the odd case. I want to look at a file in StatKey called Student Survey Exercise Hours. As you might guess, a group of college students was asked to report how many hours a week they exercise. So we're going to pull that data set up, look at the dot plot, and try to pull out the answers to these questions. So what is the mean number of hours of exercise per week? What is the median number of hours of exercise per week? And in this case, the mean is greater than the median. Could we have anticipated this just by looking at the dot plot? Is there some feature of the dot plot that would have suggested already that the mean is going to exceed the median? Let's take a look at that data set and see if we can pull out the answers to these questions. So I've pulled this data set up into StatKey. We can see that there were 361 students involved in this survey. The mean of their responses was 9.054 hours of exercise per week. The median number of hours of exercise was 8 hours per week. And in this case, as we noticed, the mean exceeds the median. Is there some feature of the dot plot that would have suggested that that would be the case? Now, all we have to do is remember that the mean is acting as a center of mass. And so these very large number of hours of exercise per week, the fact that this data set is skewed a little bit to the right, these large number of hours of exercise per week exhibited by these few students is going to pull the mean to the right. The median, on the other hand, doesn't care about those large values. It doesn't see those large values. Remember, it just sorts the list from smallest to largest and tries to cleave the list into two pieces. It's just going to find the 100, in this case, the 181st element in the sorted list and declare that that's the median. And that's happening at 8 hours of exercise per week. So once we really get attuned to the difference between the median and the mean, we would understand the influence of these very large values in our data set, and we would understand how they would push the mean to the right and leave the median sitting at 8 hours of exercise per week. Okay, now I want to take this up in some more detail here. This relates to this concept of resistance, which is where we're headed next. This is the last subsection within the section 2.2. That's the concept of resistance. One way to get into the topic of resistance is to consider an example like this. A professor gave a test. The mean score on the test was 79.24, and the median score on the test was 78. Later, she discovered that she had made a mistake. A student's score was recorded as 85, but it should have been 95. What effect will this have on the reported mean, and what effect will this have on the reported median? Let's think about the mean first. When we calculate a mean, we're just calculating a numerical average. So clearly, changing out an 85 for a 95 is only going to increase the numerical average. It's only going to increase the mean. Now, we don't know by how much. We would have to know a little bit more about the data set to see how much effect this is going to have on the mean, but we do know that it's going to be bigger than 79.24. On the other hand, the score of 85 was already in the upper half of the data set. It's larger than the median, so we know that it's in the upper half of the data set. So simply exchanging the 85 for a 95 is going to keep that value. The 95 will still stay in the upper half of the data set. And so the median is not going to be affected by that change. In fact, if we look at a very ridiculous example, if I replace that 85 by 1,000, the median is going to be unaffected. It's going to stay at 78. That number still cuts the data set into a lower half and an upper half, while the mean will go up dramatically by replacing the 85 by 1,000. So this gets at the concept of resistance. In general, we say that a statistic is resistant if it is relatively unaffected by extreme values. The median is resistant, while the mean is not. Let's take a look at this in the context of shape. So let's look and see how the shape of the data will affect the relationship between the mean and the median. If the data is skewed to the left, those values that are sitting here on the left are relatively small, and they will pull the mean down but leave the median unaffected. And so whenever we have data that is skewed to the left, we will imagine that the mean is going to be less than the median. We suspect that the mean will be less than the median. Likewise, when the data is skewed to the right, these very large values out here will pull the mean to the right of the median. We would expect the mean to exceed the median anytime the data is skewed to the right. In the case when the data is symmetric or even bell-shaped, we imagine that that vertical line, that axis of symmetry, is going to be both the mean and the median for the data set. It's going to cut the data set into a lower half and an upper half, and it's going to also act as the balance point for the data set. So in the case of symmetry or bell-shaped, we expect the mean and the median to be exactly the same. Now, I want to close this section with an example, and hopefully it'll give us some insight into how we can use the mean and the median to give us some information. And we want to know which one is better. What are some situations in which it's better to think about the median, and what are some situations in which it's better to think about the mean? All right, so here's our scenario. In Lonesome Pine, Texas, the median price of a home is $144,000, and the mean price of a home is $152,000. So here's a case where we have the mean exceeding the median. We're already suspicious that we're in a situation like this where some relatively expensive homes in Lonesome Pine, Texas are pulling the data or skewing the data to the right and pulling the mean up above the median. Okay, so what might be a plausible explanation for the difference between the median and the mean? And we're suspicious that there's probably a neighborhood or two in Lonesome Pine, Texas that has some very, very expensive homes in them, and that's going to make the mean price exceed the median price. All right, so you're a home buyer with $146,000 to spend on a home. So you've looked at your budget and you think, I can spend $146,000 on a home. Which measure of center is more helpful to you? So if you were thinking about moving to Lonesome Pine and you consulted some online figures and you saw that the median price of a home was $144,000 and you saw that the mean price of a home was $152,000, which of these is going to be more helpful to you? Now, I will argue, since you're a one-time buyer, since you're only interested in purchasing one house, the median is actually more helpful to you, because when you see that your $146,000 is slightly above the median, you realize that at least half the houses that are for sale or are going to be for sale in Lonesome Pine, Texas, are going to be available to you. You'll have half the market available to you with your $146,000 to spend. You might be somewhat discouraged by that $152,000 figure, but remember, there's those expensive homes in Lonesome Pine, Texas that you were never going to be interested in anyways, and so in some sense, this median price is more beneficial to you in understanding your prospects of finding a home in Lonesome Pine, Texas. Now, think about this situation though. You are a real estate agent trying to anticipate your yearly income. Which measure of center is more helpful to you? Now, in this case, you're not a single-time buyer. As a real estate agent, you're helping lots of people buy houses. So let's imagine that over the course of a year, you're helping people purchase houses across a whole spectrum of price levels. Your income is based on collecting a percentage of the sale price for those homes. And so you're really going to be performing a random sample from all of the houses in Lonesome Pine, Texas. In this case, this $152,000 mean price is actually closer to what you would get if you randomly sampled from Lonesome Pine, Texas, and took the average of all of the homes that you sold. So as a real estate agent, you're really going to key in on this mean price as more reflective of what your annual income is going to be. So the real difference here is the difference between a single purchase and multiple purchases. In one case, the median is more helpful, and in the other case, the mean is more helpful. All right, so that brings a close to our discussion of Section 2.2. We talked about quantity, We talked about shape. We talked about mean, median as measures of center. And then finally, we tried to talk about how the shape affects the relationship between the mean and the median. And we kind of brought this all together in this concept of resistance. So I will close off section 2.2, and I will see you once again for another video lecture on section 2.3 when we take up the concept of variation. Until then, bye-bye.